limits. The final frontier, because once you've hit a limit, you can't go any further. Okay, enough being deep, but seriously, limits are not actually the final frontier, but they're just the very beginning of a whole new branch of math that we're going to have a lot of fun delving into, which is going to be calculus. The idea of a limit is that you're saying, as some number, per se, let's say you have a function. You have the function f of x. And we'll define f of x as simply being an easy linear function, 5x plus 3. So a limit is saying, as this function approaches a certain point, what does this function equal? So as the function 5x plus 3 approaches the point, so we could write it in limit form, which is the limit of x, because it's x approaching, and we'll say as it approaches 2. As this approaches 2, for the function 5x plus 3, what does it equal? Well, it's pretty straightforward, because as you see, you've got your line. It starts with a y-intercept of 3, 1, 2, 3, and then it's going to be moving upwards at a rate of 5. So, pretty steep. So then you just follow this line along until you hit where x equals 2. You hit where x equals 2, boom, and you can say 2, that's going to be 13. So your point is 2, 13, and your limit as x approaches that is going to be 13. So now, you might ask, this looks a lot like just a really stupid, complicated way to write f of 2. Because all you're saying is you're just plugging it and solving it. Not so, good friend. Because as things get more complicated, sometimes f of 2 can be a little misleading. Take this for example. If we're going to be doing the limit of the function, we'll save that for now, limit as it approaches 0 of the function x squared plus 3x plus 2 over x, what's wrong if I just f of x that? If I put that 0 in and I say, okay, we can do this, just say f of 0, what's going to happen is I'm going to get a 0 in my denominator. No! Remember that from the functions episode? That's a big no-no, and you don't want to do that, because at which point you just broke math. Don't break math, kids. So, that being said, what a limit allows you to do is you analyze this. I'm going to put this, get rid of this too for the purpose of simplicity, or we'll just, no, I'm going to get rid of the 2. Make things faster. So, we have this, and we're saying, okay, we're going to analyze it as it approaches. That's what that arrow means, as it approaches 0. So if we were to graph this gnarly function, it would probably look, let's figure it out. So if we were to factor this, we see that you get x plus 3. And if you set x equal to 0 now, because you have no problem with the denominator, you would see that it equals 3. So we're expecting that this is going to look something along the lines of, on a graph, it's either going to be 1, 2, 3. Probably going to look something like this, or like this, which means it's going to shoot off way towards infinity before becoming undefined as it approaches this point 3, or it's going to shoot off towards negative infinity. Okay, and that's the basic idea of limits. Now, you might have asked, what did you just do, Kyle, when I did that whole? Well, let's just eliminate this, make this easier. Well, the majority of limits are caused by a 0 in the denominator. Not all of that, or not the majority of limits, the majority of asymptotes, which is when it shoots off towards infinity, and asymptotes, their location can be found with a limit. So, because the majority of asymptotes are caused by this scenario where you might have something like 5x squared plus 4x over x, you get that, and that'll cause a 0 in the denominator. and that's where you get your limit from. Or you might see something like over x minus 3. Don't let it scare you. It means pretty much the same thing. So let's take a slightly more complex situation this time. And let's say x squared minus 6x plus 9 over x minus 3. And we're going to take the limit of this as it goes towards x is 3. So how do you think we can do that? We see we've got a bit more complicated up top, so we can't just simplify it. And we want to figure out where this is going to. And the idea is, because you have that 0 that's going to pop up in the denominator at the point 3, for a limit, what you want to do is you want to divide out the denominator. And this will be important a little bit later on when we're using this for calculus. For right now, the majority of situations, you're just going to be able to easily divide it out. Unlike this one. However, if you notice, we've got a quadratic expression up top, and that can pretty easily be factored. See, x squared minus 6x plus 9. What is that? X minus 3 squared. So, drop this down, and now we have x minus 3, x minus 3 over x minus 3. So we could just cancel out 2 of those. We're left with x minus 3. Once we're left with x minus 3, we say, okay, we've got now the limit as x approaches 3 of x minus 3, which is pretty straightforward. Now you can put it in because you don't have any issues with the denominator, and you see that this equals 0. Don't be confused. The difference between having a 0 in the denominator, for example, this would equal 9 over 0, not good, versus just having a clean 0, because guess what? Sometimes your limits will equal 0. Don't let that scare you, as long as you make sure the denominator is going to equal 1, because in this situation, it's x minus 3 over 1, 0 over 1. Okay, so hopefully you feel pretty solid on limits. That's really all you need to understand, is the idea that whether your function is going to be jumping off the graph like this and heading down, it's going to be your limit is that point where it approaches. It might be an x. In fact, it's almost always an x. And for right now, we're just going to worry about x limits. So if you're looking at your x and saying, okay, with your x, what point is this approaching to, and what point is going to be undefined? Now, limits again can also be used for defined points. There's nothing to say you can't do that. For example, if a linear function, I could say, what's the limit at, we've got our Cartesian plane here, what is our limit at x equals 4? Well, we look up, boom, that's our limit. Now, what if we have a linear function with a hole in the function, which is just that little loop, and that's when you have another undefined point, but instead of being a crazy jump off the graph point where you see with the zeros in the denominators, this is typically what happens when you've already simplified an expression and you get left with just this little hole, because there's a certain point where it cannot equal. And then for this situation, you might say x equals minus 2. Well, normally this won't be defined. So for f of x, or f of negative 2, for f of negative 2, you get nope. No go, not an option, undefined, tough luck, no answer. For the limit of f approaches negative 2, it says, okay, we're approaching it, just coming up the function. Clearly, it's going to be whatever that point is on the function. Let's say it's at 3. Okay? So, you can do that with limits, and that's basically what we need to know. Now, that we're comfortable with limits, we can move on to our next section. I'm going to get off my knees for a second. We are going to jump over limits at infinity. Those are going to be your x limits. We'll come back to those a little bit later to just review them, but they're not too important for the calculus, so we're not going to worry about that for right now. And we're going to go straight on to Fun, derivatives. Not derivatives. Differentiation. There we go. Differentiation. So, the idea of differentiation is, here we go. Differentiation is saying we're going to find the slope of something. So, first things first, what's slope? You might see it rise over run. You might also know change in y over change in x, or maybe you're familiar with the form x2 minus x1, x2 over x1, y2 minus y1 over x2 minus x1. Or maybe you've heard it called gradient, slope, whatever. It goes by a lot of names, but that being said, it's not all that complicated. All it is well, it's the slope, the gradient, but right now we're going to call it the rate of change. It's the rate of change, how fast a function is getting bigger or smaller at any particular point in the function. So for a linear function, pretty simple. You guys should all know the form y equals mx plus b. It's been around for quite a while. And you know slope is m. So for a linear function, you see you got this wonderful function, and you can say, okay, my slope is just going to be m. It's going to be going up m units in the y per every 1 unit in the x. Straightforward. However, what happens when you get a function like a parabola? You no longer have a nice clean m. And this is going to be what we're working today to figure out. Now, obviously, you can use your graphing calculator, and it's perfectly easy to figure out on your graphing calculator. You go in, you say, boom, graph your nice, easy parabola. Graph your nice, easy parabola right there, x squared. And then once you graph it, all you're going to have to do is just go to calc, and then you can calculate your tangent, which is a line that goes right across, only touching one point on your function. For example, right there. We're going to imagine that touch right there. However, we want to be able to figure out a function that allows you to determine slope for your entire function depending on the x. And this is differentiation. So let's say right here, how do we know our slope? So we're saying it only is touching at one point. A close approximation to this whole only touching at one point, would be touching at 2 points, right? Because, for example, if we're looking at our tangent line, that's our actual tangent line right now, being this, and for the point, let's say we're going to make the point x. Now, we're going to create a second tangent line. Or not a tangent line, we're going to create a second line, and this is going to be an approximate. And we're going to say it's going to be for x, or for just to say between a and x. And we see this line comes down through here. It's not as close to the original tangent line, but it's not too bad either. And let's say we put another one right here, way further off. And it's going to be called, your line, oh goodness, that happens occasionally, between b and x, right there. Excuse my drawing skills. And we're going to notice that while your a and x, because they're close together on the line, is going to be more accurate, your b and x gets, it's pretty dodgy. I mean, I can take the slope of this and say, yeah, that's a slope, but we all really know it has nothing to do with what the slope actually is at this point. So, what is this telling us? It's saying that as the interval between 2 points on a function, let's draw a different function because quadratics are getting boring, so we'll go for cubic. There we go. So as the distance between those 2 points is getting smaller and smaller, the 2 points you use to define a line, like these two, the more accurate the slope gets. It goes from here to here, and to eventually until it's right along the original line. So now, you might ask why I'm not just calculating it based off a single point of touching. Remember, we're going to go back to one of our definitions of slope first, though. Because slope is change in y over change in x. Change in y equals the y of your first point minus the y of your second point minus the y of your first point, x of your second point minus the x of your first point. So, if we're saying that this is true, then how are we going to find our slope if we only have one point? It's going to be a lot harder. So we have to create this second point in order to be able to even find our slope. But we want to make the second point as close as possible to the first point. So what we're going to do is we're going to use variables here. And we're going to go quartic function this time. Just keep switching these up. And we're going to make our tangent line here. And we're going to say our point that we're trying to intersect is going to be the point x in the x direction, obviously. And then what's the y going to be? It's simply going to be f of x. This is whatever your function does to x. Because right now we're keeping this in not non-specific form. And then our second point will be x plus h, which will be a certain amount that you're moving along your x-axis, and then it's going to be the function of x plus h. Let's draw this out one more other way so you guys can see what we're doing here. And the idea is that as this h number gets smaller, this dot's going to get closer and closer down the function towards your actual x, and as they get closer and closer together, it's going to be more and more like it's simply a tangent that only touches the function at one point rather than touching the function at 2 points. So we're saying, and we're going to draw this out. Let's see, we're going to go back to quadratics. Do ourselves a nice wide quadratic right here. Get the Cartesian plane. Do this up nice and proper. And first point, x. Second point, x plus h. We look up, boom. And then we see over here, this is going to be the f of x. And over here, this is going to be f of x plus h. Because that's just your function. That's all it's saying. That your y is f of x. Thus, it makes sense to think that for x, your y is going to be f of x. And for x plus h, your y is going to be the function of x plus h. So there we go. And then we're going to take our slope between these 2 points. So, plug it back into our nifty, we'll just leave it a nifty there, into our nifty formula. And what we're going to get is your y2, which is going to be your f of x plus h minus your f of x over x plus h minus x. x2 minus xy. Now, what's the last thing we have to do? So we're going to flip back in our book right here, like, whoosh, because we cool. Okay, look back. What did we just learn? Limits. So, if we're trying to express, saying, as the distance between your first point, x, your second point, x plus h, gets smaller and smaller, then what are we saying there? As the distance or the difference between x and x plus h, the difference between x and x plus h is just going to be h. So as h gets smaller and smaller, and the space there, so between your x and x plus h, as this gets shorter, boop, then this is going to get to be a more accurate replication of what your tangent line is. Sounds a lot like limits. So what could we say? We're saying as it's getting smaller and smaller, but never quite equaling 0, because remember, we still need to have 2 points. We could say, perfectly reasonably, that this is the limit, boom, now we get to use limits again, of this for h approaching 0. H will never quite equal 0, which is a good thing, because once we say x minus x, we notice it's just going to be h on the denominator. H will never quite equal 0, however, it's going to get close to it. And then this will give us an approximation. So yay, by the way guys, you just created the original function of differentiation. This is it. So every ever differentiation function is derived off of this one. This is the big boy. Because it's saying, as your point, f of x plus h, for clear space on top here, for any function, and we'll use a cubic again, your point, f of x plus h, and f of x are going to be your 2 points here. So you're taking your line between them, boop, boop, and as h gets smaller, these 2 points are going to get closer and closer together. Or actually, more accurately, your x plus h, f of x plus h point, this one, is going to get closer and closer to your x, f of x point. Pretty straightforward. And as that happens, this is going to eventually, over infinity, as it closes in on something, is going to get close enough to the point where you can basically say, more or less, that's going to equal 0. And then this is going to work out. So, let's test this for an example here. We'll run through the example of, let's say, for the function, so what we're going to be doing is finding our slope for this function at a point. The function f of x equals x cubed, not x squared, x cubed, we're going all the way here. X cubed plus 5x squared plus 3 plus 3. We'll just leave it there. Okay, so we know that, okay? And we're going to say at the point where the slope, and we'll just write m, using that, m at slope at x equals 0. So, that being said, no, actually, I'm going to modify this a little bit so it's a bit more fun. And we'll make it plus 3x plus minus 4. There we go. Same thing-ish. So we've got our formula here. Just imagine that's still there. Still there. It's still in your head, right? Okay, keep it in your head. So we're going to plug this back into our formula. So we know we're looking at our function of, we'll leave the limit off right now, so just say big limit of h as it approaches 0, limit everything here, and then say, okay, so we have f of x plus h, but in this case, we're not actually going to be taking x plus h, we're going to be taking x equals 0 plus h. So this is just going to be the function of h, because f of 0 plus h equals f of h. I think we're copacetic on that part. So, with that, we'll write up here in our numerator h cubed plus 5h squared plus 3h minus 4. Boom. And then this is going to be minus our f of x equals 0, so f of x just equals negative 4 minus negative 4, negative 4 minus negative 4, okay? And that means negative 4 plus negative 4, and we can just get rid of that whole part right there. Goodbye. Have fun. And now, in our denominator, remember what's down there? Just an h. Just a lone h doing its thing. Boom. Okay, so this is pretty straightforward. So now, we're saying we have, oh goodness, I should have erased that so quickly. It's going to be h cubed plus 5h squared plus 3h over h. Now for limits, how do we get rid of that h? We simplify. So we get it out of the denominator by saying divide each of these by h, and that's going to give us h squared plus 5h plus 3. Okay, and now we're going to go back, h squared plus 5h plus 3, ignore the limit down here, and we're going to apply this big old limit that's been here the entire time. We've just been leaving it off to the side for the moment. So say limit as h approaches 0 of h squared plus 5h plus 3. There's nothing in the denominator to mess us up. Just get rid of all this fluff here. Nothing in the denominator now to mess us up, and we can just plug it straight in. 0 squared equals 0, 5 times 0 equals 0, 3. So this equals 3, which means for the function x cubed plus 5x squared plus 3x minus 4, the slope at x equals 0 is 3. There you go. And that is differentiating for now. Next episode, we're going to get into the particular rules that guide differentiation because, if you noticed, that took a really long time for one not really long equation. So things will get easier, I promise you. But until then, happy mathing.